Hey guys, Mr. Palmer here with a gaseous equilibrium problem, another practice problem for AP Chem. If you want to take a look at this one and try it on your own, I think it'd be good, and then you could come back and watch my explanation. I'll take you through it step by step, doing some explanations. Okay, you'll see that this one is involving ammonia, again, an ammonia gas, and this is a decomposition equilibrium. In this problem, you're given a delta H of negative 92 kilojoules. This is taking place at 450 degrees Celsius. You're given a volume of a container that's filled with only the reactant, the ammonia, at that temperature to a pressure of 20 atmospheres. It says it's heated and allowed to reach the equilibrium temperature, and the container is found to be 8 atmospheres once it reaches equilibrium. So we're going to go through this step by step. We're going to set it up. So let's take a look at the first part. You're asked to determine a partial pressure of nitrogen, one of the products, when you reach equilibrium. And you're also in part B asked to find a total pressure. So let's take a look at the equation. Most of you would say, okay, I know what I'm going to do here. This is some kind of an ice problem. So we're going to set up ICE, which stands for initial, change, and equilibrium. So in the STEM, the prompt of this problem, you're given 20 atmospheres. Now, can we set this up with pressure units rather than using molarity or moles? And the answer is yes, because pressure is going to be directly proportional to the concentration and to the moles if we're holding the temperature and we're holding the volume constant. Okay, so we can just use those pressure units just like we would any other kind of problem. And these are all gaseous reactants and products. We are told that this falls to 8, right? So it starts out at 20 initially, and at equilibrium the ammonia is 8. So it's pretty easy for us to figure out that that's going to be a change of 12. That's going down by 12. So if I come back up to this equation up here, or to our ice table, these were both initially 0, right? It was an evacuated container, nothing else was in there. This is going down by 12, we just calculated that out. So we need to look at the stoichiometry. So in our balanced chemical equation, we've got a 2-to-1 ratio. We're asked to find the partial pressure of the nitrogen. Well, if the ammonia has gone down by 12, and we have a 2-to-1 ratio, that means that the nitrogen would only be changing by 6. So it's going to be going up by 6 atmospheres, looking at the stoichiometric ratio. You could think about this as being maybe an x, and this as being a 2x, right? This would be plus x, this would be minus 2x, and it's obvious to us that x in this case would need to be 6. So that's going to give us 6 atmospheres for the partial pressure of the nitrogen. So we could say the P of the N2 at equilibrium is going to be equal to 6 atmospheres. Part B kind of continues with that, and it's asking you to determine the total pressure in the container. So for part B, right, it's finding the total pressure. I'm just going to use this same ice table for part B and go on. We've already established that the nitrogen part here, that nitrogen was the 6. Now let's look at the hydrogen stoichiometric ratio, right? If the nitrogen went up by 6, we look at the ratio here between nitrogen and hydrogen. That means hydrogen is going to be plus 3x. And we've already established that x was 6. That means 6 times 3 is going to be 18. It's going to be plus 18 atmospheres for the hydrogen. So we know that at equilibrium in our ice table, the pressure of the hydrogen is going to wind up being 18. So now in part B, it's asking us not what this pressure is, it's asking us what the total pressure is. So the other thing you have to know is that the total pressure is going to be the P of the ammonia, right? Partial pressure of ammonia, plus the partial pressure of the nitrogen, plus the partial pressure of the hydrogen. That's Dalton's law of partial pressures. So you had to find the hydrogen's partial pressure, and you have to know that you're going to add them all up. So this looks like it's 8 plus 6 plus 18, which is going to give you a total of 32 atmospheres for our total pressure in the container for parts A and B. And I would say if I was on an AP exam, I would expect that this first part, calculating nitrogen, would probably be a 2-point problem. You're asked to set up the ice table and do the stoichiometric ratio. Probably making sure you got the stoichiometric ratio, and for this actual value, that would be maybe 2 points. And for the part B, I think that's probably also a 2-point. You need to be able to calculate this partial pressure here. The hydrogen would be 1 point, and knowing that you're going to add them up to get a total pressure here, along with calculating the correct value, would probably be a 2nd point. So I'd say parts A and B, probably 4 points for that. Let's look at part C. It says write the equilibrium expression. Pretty easy, pretty straightforward. The number one problem that I think I would see that students have here is they put it in as concentration. They're going to use square brackets rather than using it as pressures, right? So we're going to take our products and we're going to put them over our reactants, raised to the power of the coefficient. So you're writing this as a pressure, not as concentration. So pressure of nitrogen times the pressure of the hydrogen, but the pressure of the hydrogen cubed, right, raised to the power of its coefficient, over the pressure of the ammonia, raised to the power of its coefficient, which is the 2. So there's our correct equilibrium expression. I'd say that's pretty easy. That's a 1 point. Calculate the value of the equilibrium constant. Wow. So now we've got to go back and we've got to take our values that we found in this step. So we've got to take our equilibrium values, whatever they happen to be for you. So if you screwed this up and you got a wrong calculation here and you got some different values, that's okay, as long as you're correctly substituting it from part B, where you found all of those, into part C's equilibrium expression. So to solve for that Kp, right, you're going to take the concentration of, or rather the pressure of the nitrogen, which we found to be 6 atmospheres. We're going to multiply that by the pressure of the hydrogen, which was 18, and that's going to be cubed. And we're going to divide that by the pressure of the ammonia, which was 8, and that's going to be squared, right, raised to that power. And if you do the math, that's going to give you 546.8, which we can round to 547. Sig figs would probably only be, 550 with correct number of significant figures. And here you don't need units, right? You don't put units on an equilibrium constant. Part E, this is asking you to apply it. Parts E and F are really good because it highlights the difference between equilibrium and Hess's law problems with delta H. So part E, we're given this equation here, right, this new equation, and we're going to relate it to the old equation. It says calculate the value of Kp for this new one. Well, how do these two relate to each other? Let's look. We can see that obviously the reactants and products have been switched. So we're taking the ammonia, we're moving it as a product, and the nitrogen and hydrogen are going to become reactants. And it's also different coefficients. It looks like all of these have been doubled. The nitrogen goes from 1 to 2, the hydrogen goes from 3 to 6, the ammonia goes from 2 to 4. So we've both doubled it and reversed it. So remember what we do. We're going to take this reaction. Remember, we had a Kp here that you've already calculated as 550, or more specifically, 547. That's before I rounded it. And we're doing two things. We're flipping it and we're changing the coefficient. So what are you going to do it? You're raising it to the power of the coefficient that you're putting in. So you're taking our initial Kp from the first one. So our Kp prime, we'll call it, of this new one, is going to be equal to the Kp of our first reaction squared, because we're going to do, we're doubling everything, and we're flipping it though. So we're going to do the reciprocal. It's 1 over. Or that could be Kp to the -2 is another way that you can write that. So you need to realize that you're going to manipulate it. You're going to put in your value. I would say this is a 2-point problem. 1 for the setup, knowing that you're going to take the reciprocal. 1 for knowing that you're going to square it and getting the correct value. So if you do that, and in fact, I don't think I did that. Let me quickly get that on my calculator. 547 squared, and I'm going to take the reciprocal. Looks like I'm going to get 3.3 times 10 to the negative 6 power. Okay? Awesome. And one last problem here. Let's take a look at this one. F. Based on the molar enthalpy of negative 92 kilojoules for the decomposition of ammonia in parts A through D, the one that we had right here, I'm going to rewrite this. Here was our molar enthalpy. It's asked you to determine the molar enthalpy change for the reaction in part E, the one that we just looked at up here. So again, what did we do to that problem? We had reversed this one, and we multiplied everything by 2. So this highlights the difference between equilibrium and enthalpy. In enthalpy changes, remember, we don't do the reciprocal and raise it to a power. We're going to do whatever we've done to the reaction. So we've reversed this one. So that means we're going to take the delta H of our original. We are going to change the sign. We're going to reverse it. And we're going to multiply it by 2. So we're going to essentially take our delta H and multiply it by negative 2. So we're going to reverse it. This was negative, so the sign is going to change. It's going to become positive. And we had 92, right? So 2 times 92 kilojoules is going to give us 184 kilojoules per mole of reactant, and that's going to be a positive value. I'd say this would probably be a 2-point problem again, knowing that you have to take your delta H, double it, and change the sign. So making sure that you had the correct sign with that value and that you did the doubling part. All right, that's it for this one. I'll be back with another one soon, guys.